Hi, my name is Drew Buck. I'm a researcher at the University of Missouri, and in this video I'm going to show how you can use AirSim to do 3D point cloud reconstruction of a simulated environment. So I'll link to the Git repository for this example in the video description below, and if you follow that link you can download the code that we'll use. In the repository there's a README file that will describe everything that we're going to cover in this video. So the first thing that we need to do is install AirSim and set up our Python environment. So AirSim is a plugin for the Unreal Engine developed by Microsoft that allows us to simulate a virtual drone or car in a simulated environment and control it with a scripting interface. Now, if you're going to use this in your own custom projects, you'll want to build it from source, but today we're just going to download a precompiled binary environment. So they provide several precompiled environments that we can use. I'm going to use the AirSim neighborhood pack today. It's about 1.5 gigabytes, so it will take some time to download. But once you download that and unzip it, you'll have this executable file that you can run. So if I run that, the first time it's going to ask if I want to use a car or quad rotor simulation. So I'll hit no to use the quad rotor. But really what we're interested in is the computer vision mode. So I'm going to exit this with Alt F4. And the first time I run that, it will create a new directory in my documents folder under my user home directory called AirSim with a settings file. The settings file that it creates by default is pretty minimal, and so what we'll need to do is copy in the settings file from our repository and replace the original settings file. And this new settings file defines a lot more options. It sets the simulation mode to computer vision mode, and it defines 3 cameras that we're going to use to collect imagery. We're going to collect color imagery, depth imagery, and segmentation imagery. And we can define the parameters for each of those cameras. We've defined a width and height of 256 by 192 pixels and a field of view of 90 degrees. And you can adjust those as you need for your own applications. So now if I go back and run the AirSim executable again, I'll get this first person view, and I can press F1 to list all of the keyboard shortcuts. So basically I can control the camera with commands such as page up, page down to go up and down. The arrow keys let me go forward, backward, left, and right. I can use the A key, the D key to yaw, and W and S to pitch the camera. And then backspace will reset everything back to the origin. If I hit the R key, that will start recording. So it's configured to only record when the camera moves. So once I start moving, it will begin recording every frame onto my computer. So maybe I want to record a sequence where I move down this road and I go down this road, and maybe I come out here and I rise up a little and pitch down and do some kind of orbit maneuver just like this. So if you can get comfortable with the keyboard controls, you can do your data collection that way. And I'll hit R to stop recording. It does take a little bit of practice, I think, to become familiar with those controls. And so we'll talk about another way to script that recording in just a bit. But what that does is that creates a folder with a timestamp. And if I look at this folder, there's an AirSim rec file here that has all of the camera parameters for each frame that it captured. It has the location and the orientation of the camera for every frame, so we'll make use of that in our reconstruction script in just a bit. It also saves out the images for every frame. The color images are saved. The segmentation labels for each object are saved. and we also save the depth imagery in a floating point format that's a little difficult to visualize. So if I want to reconstruct this run into a point cloud, what I can do is run one of the reconstruction scripts that is in the repository. So to do that, I'll need to set up my Python environment. So I've already created a Conda workspace. So I'll activate that now. And you can see the Python version I'm using is 3.8, and that's for compatibility with Open3D and AirSim. Now, getting both of those packages to work at the same time, there's some dependency conflicts. So my suggestion is to install Open3D first. So do pip install Open3D. I've already got it installed, so it goes pretty quickly, but you'll see that there's some errors with the dependencies with regard to message pack and tornado. If I then pip install AirSim, it will downgrade the tornado version to an older version that it's compatible with, but it will break some of the things that Open3D installed. So we're not going to use those things. But we'll also need a couple other packages that you may already have installed. We'll need pandas to load in the CSV file of the camera poses. We'll need pillow to open the images, and TQDM to display our progress bar. And so I've already got those installed. So now what I can do is I can run the reconstruct script, and I'll just take a look at that. So what that's going to do is it's going to load in one of these runs that we've collected with AirSim, and it's going to loop over every one of those frames. It's going to take the camera parameters and transform it into a coordinate system that's a little more familiar for point cloud reconstruction, and it will load the images, reconstruct the point clouds, and save them to disk. So I can run that with Python AirSim reconstruct.py, and if I do -h, that will just list all of the commands I can use. So this first one I'm going to do -l to run the last run, and I'll include the viz flag so that we can visualize it at the end. So it will loop over all those frames, and this is the reconstructed point cloud from the sequence that we just manually recorded. You can see all of the camera positions that it's using. I can adjust the point size with the plus and minus keys here in this Open3D window. And so you can imagine how this could be really useful to a computer vision researcher, as having access to this point cloud data. So if I go back to my AirSim directory in this run, that script has also created a PCD file, which is the point cloud data file, and I can open that in another program such as Cloud Compare. And so I can definitely make use of that data in other programs. Now, something that might be really useful is if we include the W flag, and what that will do is it will write a separate point cloud for each frame of the sequence. So that will create a new directory called points, and in there I have a list of camera parameters. Each one of these is a JSON file that's in the Open3D data format, so you can load this with Open3D and have access to the camera intrinsic and extrinsic parameters. And it also will save the point cloud for each frame. So if I load this in to my into Cloud Compare here, you can see that it's just one frame of that entire sequence. So if I'm not able to control the camera very well, what I might want to do instead of manually recording it is I might want to script a collection. So I have another script here that will do a lawnmower pattern within a certain region. So I've got it defined here to do plus or minus 100 meters around the origin point. It's going to step 50 meters between each image and do it at an altitude of 50 meters. And so there's some stuff here to set up the initial pose to look straight down and connect to AirSim, creating this client object, and begin recording. And then I iterate over each of those waypoints, updating the pose, and I pass that pose to AirSim with the updated XYZ and the roll, pitch, and yaw. And I include a short time delay to make sure that the Unreal Engine can render the assets that it needs when you move the camera quickly, and also that it can save that data to disk. When we're done with that, we stop recording. And so if I run this now, I want to make sure that my AirSim environment is still running. And then I can run AirSim collect, and that will automatically move the camera and create a new recording with just the images that we've specified. So now if I do my reconstruction, we'll get a nice view of that whole scene, and you can see that the camera positions are in a nice regular grid pattern. Since we're looking straight down, obviously we're not going to see the sides of buildings in this example, so we would need to update that script to include a more complicated trajectory if we wanted to look at the sides of objects, for instance. Now the other thing I can do is include the seg flag, and that will do the same thing again, but this time using the segmentation labels of the objects. And so this will allow me to use this for ground truth, for object detection, for instance, by having a label for every point in that image. So that saves a separate point cloud. I can look at these, turn these off. I can look at these in Cloud Compare and see that they are visible in other programs. I have a shader enabled to make it a little easier to see those points. And we also have the per frame point cloud. So we have just the segmentation for a particular frame. We can get the color for a particular frame. And we can do all sorts of interesting things with this data. So thanks for listening. I'm really excited to see what everybody can do with this approach. Thank you.